Okay, let's see. We are starting with some review of section 3.4, and then we'll look at some things from section 3.5. And section 3.4, we're looking at problem number 91, which is solving ln of x plus ln of x minus 2 equals 1. Is that right? Did I copy that correctly? All right. And this is number 91 from section 3.4. And so we would rewrite this first using the quotient rule. So we would write this as ln of x over x minus 2 equals 1. And then I would solve this by rewriting this in exponential form. So what's that going to look like? Bailey, how do we rewrite that in exponential form? Pardon me? We're going to rewrite this one, which is currently in log form. We want to rewrite it in exponential form. Was it a plus? Where, here or here? Oh, well, that changes everything, Billy. All right, so this is supposed to be a plus right there, but that's still a minus. All right, that is going to change things. So this is a plus. That means we need to use the product rule, not the quotient rule. So this is going to be x times x minus 2. Thank you, Billy, for being quality control today. All right, so remember, this is really, when you see ln, that's log to the base e. In this case of, I can distribute and say x squared minus 2x equals 1, and that's still log form. All right, that's our log form. So we want to rewrite this in exponential form. So Bailey, how would we do that? E to the first equals x squared minus 2x. And so then we would want to solve this. So I would subtract e from both sides. And so I would get 0 equals x squared minus 2x minus e. And I would actually, I mean, we could try and solve this by factoring, but that's not going to work. So we're going to need to use quadratic formula on this. So we would do, opposite of b, which would be opposite of a negative 2, plus or minus square root of b squared minus 4 times a, which is 1, times c, which is negative e, all over 2a. So that's all over 2 times 1. Hello. I'm assuming that's your calculator? Okay. All right. And so we have 2 plus or minus square root of 4, what is that, plus 4e over 2. And I guess the bottom line is I would just get decimal approximations for these. Did anybody do that? Negative 0.928 or 2.928. Okay, so if those are our two answers, are they both okay? Can we use both of them in the original? No, why not? I can't take the log of a negative number, so we cannot use that first negative one because then we're going to be undefined with those logarithms. But the second one is okay, so this is going to be our solution here. That one's going to be extraneous. All right, anything else from section 3.4? Pardon me? 98. 98. Log x plus log x plus 2 equals log x plus 6. Log to the base 2 of x plus log to the base 2 of, what was it? X plus 2 here equals, is it x plus 6 here? Is that right? Okay, and so again, we would use the product property. So log to the base 2 of x times x plus 2 here equals log to the base 2 of x plus 6. And since I have log to the base 2 on both sides of the equation, I can just rewrite this as, in this case, x squared plus 2x would have to equal x plus 6. And I would suggest that you get everything over on one side. So subtracting x's, subtracting 6, I would get 0 equals x squared plus x minus 6. That factors into what? Is that a plus 3 and a minus 2? Does that look right? And so our solutions are going to be x equals 2 or x equals negative 3. Are those both okay? Or are one of those extraneous or both of them extraneous? Yeah, we can't use negative 3 because we can't take the log of a negative number, and that would be a negative, and well, that one would be positive, but these two are going to be no good. So we would say this one is extraneous. Oh, that was not nice. This one would be extraneous here, and we would just take this as our solution. All right, let's look at a few things from section 3. 105. Okay, so if we graph 3 minus ln of x, you have your calculators. If we do, whoops, if we, documents, graphs page, I want to graph 3 minus ln of x. All right, I'm graphing this, and I want to know when is 3 minus ln of x equal to 0. So I might want to see what's happening further out here for the graph. So if I kind of pull this, it sure looks like it's crossing right about here, right? I just dragged it over a little bit to see. And I can do menu, analyze, graph, 0, and it looks to me like it's occurring at 20.1, comma 0. Do people agree with that? And I can check that on Scratchpad if I do 3 minus ln of 20.1, 3 minus ln of 20.1, it should be pretty close to 0. And that's not bad. That's pretty close. Are we okay with this? All right. And then were you asked to solve it? And solve. Yeah, I guess that was it. Okay, at this point, let's look at some things on section 10.5. I'm sorry, 3.5, excuse me, 3.5, exponential and logarithmic models. So we already talked about some of these things last time. We looked at a population example last class, and we did look at the fruit fly problem last class. Is that correct? Yes? Did we do this one, number 3, on the gift? Yes, we did that one. Okay, and did we do this one? No? Okay, all right, so the value of b in the exponential decay model, y equals a times e to the negative bt, determines the decay of the radioactive isotopes. So find how much of an initial 10 grams of 226 radium isotope with a half-life of 1,599 years is left after 500 years. So this one I don't think is on your gift, right? So let's put this one on paper, and then you've got one on your gift that you can try later. So for this one, if we are going to find the amount left after 500 years, we'll start with our decay model, and we're going to plug in the half-life. The only thing we know is that the half-life is 1,599 years, so that half-life is going to go right here, right? The initial amount, 10 grams, goes right here, right? And we know that after 1,599 years, since that's the half-life, we will have half of what we started with. And so that's why I can write half of 10, which is really equal to 5, right? So my 10 grams is going to be down to 5 grams after 1,599 years. Does that make sense? Okay, and then we need to solve this equation. The equation was 5 equals 10 e to the negative b times 1,599. So what would be our first step in solving this? Brendan, we're doing this on paper. Put phone away, take paper out. All right. So Brendan, what's going to be our first step in solving this? No, we have to solve for b. So we're not plugging into a calculator. Perfect. So let's divide both sides by 10. So we're going to get 0.5 or 1/2 equals e to the negative b times 1,599. All right, what's going to be our next step here, Jack? We cannot divide by e. What are we going to do? This is in exponential form. We need to rewrite it in log form. So Jack, what's that going to look like in log form? Okay, ln or log to the base e. I'm with you.
0.5
Of 0.5.
equals negative b.
All right. And so if that's our case, that we've got ln of 0.5 equaling negative b times 1,599, what would be our next step? Again, we're trying to solve for b. Billy. All right. Can we divide by a negative 1,599? All right, we're going to divide both sides by a negative 1,599. So with your calculators, would you do that now, please? You're going to do ln of 0.5 over negative 1,599, because this is dividing out. The negatives are becoming positive, and we're getting b is approximately what? All right, let's see, I'm making Bailey live presenter. So Bailey has ln of 0.5 over negative 1,599, and you got 0.000433. Everybody agree? All right, so if that's our b value, 0.000433, is that right? Okay, so that means in our model, when we go back up here, we're going to fill that in for b here. So our model is really y equals a times e to the negative 0.00043t. And I actually do want to also fill in our initial amount, because we were told that. What was our initial amount in this problem? I have it hidden. 10. All right, so I really have y equals, curse you, smartboard, y equals 10 times e to the negative 0.00043t. Now that we have our model, and we had to do a lot of work to get that, now we can answer the question, which is how much of an initial amount is left after 500 years. So Bailey, how do we figure that out? Plug in 500 for t. So we're going to plug in 500 right here. Go ahead and work that out on your calculator. Let's see. Fresh. All right, let's see. Billy, do you have this? So 10 times e to the negative 4.3 e to the negative 4. I think that sounds good. Times 500. So 8 grams approximately. Do people agree with that? All right, so there would be 8 grams remaining when we plug that in. All right. Okay, let's take a look at the next example. A certain radioactive isotope has a half-life of 24,100 years. This is on your gift. After 24,100 years. After 1,000 years, there's 2.1 grams remaining. What was the initial quantity? So in this case, you're not given the initial quantity. So let's just write down our model. y equals a times e to the negative bt. Well, we don't know what the a is, and we don't know what the b is, so we're really left, the only thing we can do is we can plug in the half-life, because that is useful information. So the 24,100 is going to go in right here. We can make up something here. Make up an initial amount. Doesn't matter what it is, you're just making it up for right now to help you get one of the constants. But if we make up an initial amount, like let's say, I'm just making this up, 20 grams as my initial amount, then how much will be remaining after the 24,100 years? 10, right? Half of the original. So then I would put, then this will be 10 grams, right, after the half-life of 24,100 years. So go ahead and plug those values in so we can solve for one of the variables. So we are going to write 10 equals 20 times e to the negative b times 24,100. And what would we do to solve this? First step here, Jack? Dividing by 20, so we end up getting 0.5 equals e to the negative 24,100b. Hello? Cord? Yes. All right, that's got my name on it, so I know that's coming back. Thank you. All right, next step would be what, Brendan? All right, what's it going to look like in log form? So log to the base e or ln, either one, of what? Of 0.5. All right. Okay, so if that's the case, now our last step is going to be to divide both sides by negative 24,100. Would you do that on your calculators, please? Let's see what we get for the constant b in this problem. So we have just what, 0.0004 zeros in a 2-9? Does that look right? Everybody agreeing? All right, so if b turns out to be 0.000029, now when we write our model, we're going to fill that in. Come on. Fill that in for the b. So we're going to have y equals a times e to the negative 0.000029 t. All right? And we now know that we are told that after 1,000 years, there will be 2.1 grams remaining. So what are we going to do with the 1,000? What are we going to do with the 2.1? Bailey? All right, so 1,000 is going in for the t, and the 2.1 is a. Do people agree with that? Why would 2.1 be y? All right, it's the amount remaining, so let's plug the 2.1 in for y, because we don't know the initial amount. We're asked to find the initial amount, and the initial amount is a. So our equation is going to be, if I can squeeze this in here, 2.1 equals a times e to the negative 0.000029 times 1,000. All right, and I'm going to need a little bit more room to work here with this. Oh, good, it's all coming together here. All right, so now that I have this, what would be our first step here? Can we just multiply this by 1,000? Is that going to just slide this decimal place over 3 spots? So I'll have 2.1 equals a times e to the negative. Is it going to be a 0.029? Like that? Okay, so how do we solve for a? All right, we're going to divide both sides by e to the negative 0.029. Does that sound right? So what is 2.1 divided by e to the negative 0.029? Do that on your calculator, please. Brendan, you got this? You got 2.16179. So really, we only started with 2.16 grams, and after 1,000 years, it's only down to 2.1 grams. So only lost like 1/100th of a gram, well, 6/100ths of a gram, right? But that's makes sense because the half-life is 24,000 years. So after 1,000 years, you're not losing that much. Okay, so that looks good for that one. So that's going to be our answer. 2.16179 was the original amount. All right, number of grams. What's next? Okay, Gaussian models are used in probability and statistics to represent populations that are normally distributed, like the normal distribution that you would learn about if you took a statistics class. The average value for a population can be found from the bell-shaped curve by observing where the maximum y value occurs. The x value corresponding to the maximum y value represents the average value of the independent variable. All right, let's take a look at example 4 on page 261. Got your books with you? All right, on page 261, example 4, it says in 2004, the SAT math scores for college-bound seniors roughly followed the normal distribution given by that Gaussian model, where X is between 200 and 800, and that's the SAT score for mathematics. Sketch the graph of this function. From the graph, estimate the average SAT score. So if you look at the graph, it's a bell-shaped curve, and the maximum value of the curve represents the average score. And you could do this on your calculator. Just do menu, analyze maximum, and it looks like it would occur at about 518. All right, so with that in mind, let's take a look at this example. No, I thought there was one on your, do you not have one on your gift? Did I put one like this on your gift or no? Maybe not. Is it? Uh-huh. All right, let's do number 5 on the gift. So would you take a moment to type that into your calculator? It says last year the math scores for students in a particular math class roughly followed the normal distribution. So you're doing this on a graphs page, right? It says look at the graph on the TI Nspire and use it to estimate the average math score. All right, so Billy, I made you live presenter. You're going 30 to 110, and let's do y minimum. Go 0 to 1, and let's see what the graph looks like. All right, do you see how we can see from Billy's graph that we have just this little bit of the graph right here? So instead of 0 to 1, let's make it 0 to 0.1 for your y maximum. All right, so that's looking a little bit better. We could even say 0.05 or something like that. But anyway, at this point, we can see that here are the scores on this test. And at this point, we could find the maximum. Can you do that? Menu, analyze, maximum. All right, and what's it turning out to be? 74? So what is the average math score? The average math score would have been 74% on this exam. Are we okay with this? All right, let me see what's, I'm going to take a look at each one of your graphs. Where's your graph? Jack, what happened to your graph? Disappeared. Brendan, let's see your graph. I can creep on everybody's graph today. Oh, what'd you do? 30, that said the domain, 30 to 110 for the, 30. I know the pressure, you're on the big screen here. 30 to 110. And then for y minimum, 0, and y max, why don't you do like 0.05. There you go. Okay. All right, there's your graph. And now you can do menu, analyze, and maximum. Let's see. Jack, do you have your graph now? You're just adjusting the window? All right, and Brendan's got the graph. Bailey, you got this graph? All right, looks good. Okay. All right, at this point, let's go on to look at the next example. All right, so logistic growth models. Some populations initially have rapid growth followed by a declining rate of growth. One model that describes this growth pattern is the logistic curve. Another name for a logistic growth curve is a sigmoidal curve. There is a graph on page 262. Would you take a look at that, please? 262. Do you see how that top graph on page 262, there are two horizontal asymptotes, because it starts out kind of slowly and then it really picks up speed, and then it kind of levels off at some point and approaches another horizontal asymptote. So let's take a look at number 6 on the gift. The problem involves one of these logistics curves. It says on a college campus of 7,500 students, one student returns from vacation with a contagious and long-lasting flu virus. Yuck. All right, the spread of the virus is modeled by that equation where t is greater than or equal to 0. Y is the total number of students affected after t days. So the college will cancel classes when 30% or more of the students are infected. So how many students will be infected after 4 days? I tell you what, for this purpose, instead of just entering this on a calculator page and entering 4, let's graph this one carefully on a graphs page. So go to a graphs page, type that one in. I'm going to pause this so people watching at home can type this in also. Okay, after that long pause where I forgot to unpause, let's back up to see a little bit of what we talked about. I don't even remember where we left off. I'm just going to take it from number 6, I guess, and I'm going to count on my students here to still have the graph up. So we graphed this college campus contagion, which I don't even think we were on this problem. I think we were one before it. All right, let me back up. Oh, that's right. And I didn't have this one on the screen, but you typed it in, right? I hope one of you still has that. You weren't doing this all on Scratchpad, were you? Billy, you got this? Oh, good. All right, Billy, can you call this one up where we did the mean SAT scores or math scores for a particular math exam? So Billy has this somewhere. Let's see. All right, so when you graph this, we graph from 30 to 110, and we had to change this y to like 0 to what? Like 0.1. Can you just show your window settings? Don't change them at all, just show the Windows zoom settings. All right, so 30 to 110, and then 0 to 0.1. Okay, that's good. Say okay. And then we did menu, analyze, maximum, and we saw that the maximum was at 74. Okay, then we moved on to problem number 6, which was the college campus problem. And for this problem, let's see, we graphed this. I'm going to stop this. Let's see, Bailey, do you still have this? Was I having you as the live presenter? All right, so Bailey typed in this function, and we did menu, trace, graph trace, and we found out that after 4 days it was only 36 students affected. Is that right? And then we wanted to find out when was the school going to cancel classes, so we had to take 30% of the student body, so 30% of 7,500, which was about 2,250. So we entered that line right here. This is that second function that you see here. It's just this horizontal line of 2,250, and then we did menu, analyze, and intersection, and we found that the intersection was right here at this ordered pair. No, that's not the ordered pair. Was it? The ordered pair was this one, 8.97, comma, 2,250. So after approximately, after about 9 days, the college would have to cancel classes, right? Okay, now that hopefully we're back on track, that was the speed version of that. Let's see. So we looked at that one. All right, so we're talking about logarithmic models. On the Richter scale, the magnitude R of an earthquake of intensity I is given by R equals log I divided by I sub 0. Those are I's, not ones. I represents the measure of wave energy, and I sub 0 is used as the minimum intensity. It's used for comparison purposes, and we just use 1 for the I sub 0. So let's take a look at this example. Find the intensities per unit of area for each typo earthquake. All right, so there was an earthquake in northern Sumatra in 2004, which was really powerful, had a Richter scale rating of 9.0. So if we're going to find the energy released for this, right, the intensity of this, we're going to use this formula. So we're going to do R equals log I over I sub 0, but we're just going to plug in 1 for this I sub 0, right? That's just the number 1, and our Richter scale rating is 9 in this example. So how would we, and I over 1 obviously is just I, so I can write this as 9 equals log I. So how do I solve for I to find the intensity? Brendan. All right, so let's write it in exponential form. I need a little bit more room here. Let me slide this down. All right, so if we're going to write this in exponential form, what would that look like? I don't see a base here, Brendan, so what base is it? Base 10. So what am I going to write? Well, this is already log to the base 10. This is log form. We want to put it in exponential form. So what's our base? 10, right, is our base. So 10 raised to what power? 9 equals I. So the intensity would be, that's supposed to be an I, would be 9 zeros, correct? So is that 1 billion? Would you agree? 10 to the 9th? All right, so 1 billion, I don't know if they, did we talk about what units that would be measured in? Just the wave energy, a measure of the wave energy. All right, and so if we compare that to the earthquake in Alaska in that same year that had a rating of 6.8, what would be the intensity of that one? So we want 6.8 equals log I, and rewriting this one, Bailey, what would we do? 10 to the 6.8 equals I. And what is 10 to the 6.8 on your calculator? E6. So that's really 6, 3, 1, 2, 3, 4, 5, 6. So that's going to be 6,310,000. All right, so quite a difference from 1 billion. All right, let's see. Okay, so now let's try this one. This one's on your gift. This we're doing the other direction. So find the magnitude R of an earthquake of given intensity. So if the intensity is 68,400, now again we're using our model. R equals log of I over I sub 0, but I sub 0 is just, we just use 1 for that. And so in this case, we want R equaling log of 68,400,000. And what does that turn out to be? Clear this ink. All right, so we get log to the base 10 of 68,400,000 is about 7.8. So our Richter scale rating for this one would be about 7.8. All right, and what if it's 42,275? And what does that one turn out to be? 7.6? About 7.63, for example, on the Richter scale. All right. So that completes our notes on section 3.5, and we're going to have a homework assignment about that, and whatever you have not finished on the gift, I would ask you to finish it at this time. All right, and that's it for now. I hope that if you were not here with us and you were watching this video, that this was helpful. Sorry that it was 37 minutes long. It probably should have been a little bit longer, but I paused you for too long. So, all right, have a good weekend, everybody.